In 1883, engineers built a bridge so advanced it used technology we didn't fully understand until the 1960s. The Brooklyn Bridge wasn't just ahead of its time, it was performing calculations its own builders couldn't explain. And it's not alone. Today, we're uncovering 5 19th century bridges that defy everything we thought we knew about Victorian engineering. The 19th century gave us steam power, the telegraph, and the Industrial Revolution. But while we celebrate these innovations, we often overlook the most incredible engineering marvels of the era. Bridges that push the boundaries of physics, mathematics, and material science in ways that seem almost impossible. These structures weren't just built to last, they were built using principles that wouldn't be formally understood for another century. Today, we're diving deep into 5 bridges that have left modern engineers scratching their heads, asking one simple question: how did they do it? Let's find out. Bridge number 1, the Brooklyn Bridge, the pneumatic wonder. Our first stop is perhaps the most iconic bridge in America, the Brooklyn Bridge. Completed in 1883, this Gothic revival masterpiece connects Manhattan and Brooklyn across the East River. But here's what most people don't know. This bridge pioneered a construction technique so dangerous and so advanced that it literally rewrote the rules of underwater engineering. John Augustus Roebling, the bridge's visionary designer, faced an impossible challenge. How do you build foundations for massive stone towers in a riverbed 78 feet underwater? His solution was revolutionary: pneumatic caissons. These were enormous wooden boxes the size of city blocks that would be sunk to the river floor. Here's where it gets incredible. Inside these caissons, workers would dig out mud and rock while compressed air kept the water out. Think about this. In the 1870s, before we understood decompression sickness, before we had proper diving equipment, men were working in pressurized chambers at depths that would make modern OSHA inspectors faint. The pressure was so intense that when workers emerged too quickly, they suffered from what they called caisson disease, what we now know as the bends. Even Roebling's own son, Washington Roebling, who took over after his father's death, was permanently disabled by the condition. But here's what's truly advanced about this bridge: the cable design. The Brooklyn Bridge uses a hybrid cable-stayed and suspension system that distributes load in ways that engineers didn't fully mathematically model until the computer age. Each of the 4 main cables contains 5,434 individual wires bound together with a technique called cable spinning that Roebling essentially invented. Modern analysis shows these cables handled dynamic loads, wind, traffic, vibration, with a sophistication that suggests Roebling had an intuitive grasp of resonance frequency and harmonic motion that wouldn't be formally quantified until the 20th century. The Brooklyn Bridge has survived hurricanes, blizzards, a century and a half of traffic, and even a stampede of elephants. Yes, that actually happened in 1884, when P.T. Barnum walked 21 elephants across it to prove its strength. And it's still standing, still functional, still carrying 120,000 vehicles and thousands of pedestrians every single day. Bridge number 2, the 4th bridge, the cantilever giant. If the Brooklyn Bridge pushed the limits of cable engineering, the 4th bridge in Scotland completely revolutionized how we think about steel structures. Completed in 1890, this railway bridge is so massive, so over-engineered, that it's essentially a monument to Victorian paranoia and brilliant engineering. To understand why, we need to talk about tragedy. In 1879, the Tay Bridge in Scotland collapsed during a storm, killing 75 people. The disaster shocked the world and terrified bridge designers. When engineers Benjamin Baker and John Fowler were tasked with building a new bridge across the Firth of Forth, they had one mandate: make sure, absolutely sure, it never ever falls down. Their solution was the cantilever design: 3 enormous double cantilever structures, each jutting out from massive piers. But the scale is where this bridge becomes absurd. Each cantilever arm extends 1,700 feet. The entire structure uses 58,000 tons of steel, held together by 6.5 million rivets. Let me put that in perspective. If you started removing 1 rivet every minute, it would take you over 12 years to take them all out. But here's what makes this bridge truly advanced: the stress analysis. Baker and Fowler didn't just build this bridge to handle trains, they designed it to withstand wind loads that wouldn't occur for centuries. Their calculations for wind stress, lateral forces, and dynamic loading were so far ahead of their time that when engineers reanalyzed the bridge in the 1960s using computers, they found the original Victorian calculations were essentially perfect. The bridge was designed for wind speeds up to 125 miles per hour. At the time, there was no such thing as a wind tunnel, no computational fluid dynamics, no computer modeling. Baker used pure mathematics, physical models, and an almost supernatural intuition about how forces flow through tubular steel. There's a famous photograph from 1887 showing Baker himself demonstrating the cantilever principle using two men sitting on chairs, extending their arms, while a third man sits suspended between them. It's a simple demonstration of an incredibly complex structural principle, one that would become the basis for countless bridges worldwide. Today, the Fourth Bridge is a UNESCO World Heritage Site. It carries 200 trains every day, weighing up to 1,000 tons each. It's been in continuous operation for 134 years. And perhaps most remarkably, it's never had a structural failure, not one. The Victorian engineers who designed it were so cautious, so thorough, that they accidentally built a bridge for the 22nd century. Bridge number 4, the Royal Albert Bridge, Brunel's swan song. Isambard Kingdom Brunel is a legend in engineering circles. Tunnels, railways, ships, and bridges that redefined what was possible. But the Royal Albert Bridge, completed in 1859, might be his most ingenious creation. And tragically, it was also his last. Brunel faced a unique challenge: cross the River Tamar between Devon and Cornwall with a single-span bridge high enough for naval ships to pass underneath, strong enough to carry heavy trains, but light enough not to collapse under its own weight. Oh, and he had to do it on a shoestring budget. His solution was so radical that no one had ever tried it before: a hybrid truss suspension design that combined arched tubes with suspension chains. Imagine a bridge that's simultaneously pushing and pulling, compressing and tensioning, all in perfect balance. The top tube is in compression, it's being squeezed. The bottom chains are in tension, they're being pulled. Between them, the vertical and diagonal members transfer the load of the trains. It's a symphony of forces, all working together. But here's where Brunel's genius really shines: the tubes themselves. They're not solid iron. They're made of wrought iron plates riveted together into massive oval tubes, each 16 feet in diameter. This gives them incredible strength-to-weight ratio, something we now recognize as a fundamental principle of aerospace engineering. Brunel essentially invented the monocoque structure, a hollow shell that resists forces through its shape rather than its mass. The same principle is used in airplane fuselages and spacecraft today. Construction was a nightmare. The tubes were assembled on the shore, then floated into position during high tide. Each tube weighed over 1,000 tons. The operation required split-second timing and nerves of steel. One mistake, one miscalculation, and the entire structure would have sunk to the bottom of the Tamar. They pulled it off perfectly. Brunel was so ill during construction that he could barely visit the site. By the time the bridge was complete, he was dying. He had himself carried across it on a special couch, inspecting his final masterpiece one last time. Narrator: the Royal Albert Bridge has carried trains for 165 years. It's still the main rail link between Devon and Cornwall. And when engineers analyzed it using modern computational methods, they discovered that Brunel's design had a safety factor of 3.2, meaning it's more than 3 times stronger than it needs to be. For a man working with slide rules and intuition, that's not just impressive, that's supernatural. Bridge number 5, the Eads Bridge, the steel pioneer. Our final bridge might be the most important one you've never heard of. The Eads Bridge in St. Louis, completed in 1874, was the first major bridge built entirely of steel. Not wrought iron, not cast iron, steel. And in doing so, it literally created the modern steel industry. James Buchanan Eads was not a bridge engineer. He was a salvage diver and self-taught engineer who had never built a bridge before.
When he proposed spanning the Mississippi River at St. Louis, professional engineers told him it was impossible. The river was too wide, too deep, too violent. Eads ignored them. His design called for 3 arches, the longest spanning 520 feet, unprecedented for the time. But more radical than the arches was his choice of material, steel. In 1867, when construction began, there was no such thing as structural steel. It simply didn't exist as a commercial product. So, Eads invented it. Working with steel manufacturers, he developed specifications for structural steel alloys and quality control processes that became the industry standard. Every steel beam, every component was tested. Eads personally supervised the destruction of sample pieces to verify they met his requirements. He rejected 20% of the steel delivered to the site. In the 1870s, that was unheard of, but Eads knew that if steel failed on this bridge, it would set the industry back decades.
Like the Brooklyn Bridge, the Eads Bridge used pneumatic caissons. In fact, Eads pioneered the technique in America before Roebling used it in New York. Workers descended 100 feet below the riverbed, deeper than anyone had gone before. The pressure was so intense that candles wouldn't burn. There wasn't enough oxygen. 14 men died during construction, mostly from caisson disease. It was a brutal education in the physics of pressure and human physiology. But when the bridge opened in 1874, it was a marvel. The arches were so precisely engineered that when Eads calculated how much the bridge would rise after the temporary supports were removed, he predicted it would lift exactly 3/8 of an inch. It rose exactly 3/8 of an inch. The Eads Bridge proved that steel could be trusted for major structures. Within 20 years, steel had replaced iron in bridge construction worldwide. The modern skyline, the skyscraper, the suspension bridge, all of it traces back to this bridge in St. Louis. And it's still carrying traffic, cars on the upper deck, the Metrolink light rail on the lower deck. After 150 years, it's as solid as the day it was built. So what do these 5 bridges teach us? They reveal something profound about human ingenuity. The engineers of the 19th century didn't have computers, finite element analysis, or computer-aided design. They had slide rules, drawings, and mathematical intuition. But what they also had was something we've lost in the age of software. They understood forces. They felt the weight, the stress, the tension in their bones. They built physical models. They tested to destruction. They learned from failures. Their knowledge was empirical and hard-won. Today, we can model anything. But when modern engineers study these Victorian bridges, they find them almost perfectly optimized. The computer calculations match the 19th century mathematics. The lesson? Technology amplifies our abilities, but it doesn't replace intuition, craftsmanship, or the willingness to push boundaries. These bridges weren't just ahead of their time, they were timeless, built with principles so fundamental, so well understood that they transcend the era that created them. And perhaps that's the real secret. True engineering isn't about the tools you have, it's about understanding the fundamental forces of nature and finding elegant ways to work with them. These 5 bridges are still standing, still teaching, still inspiring. They're monuments not to Victorian technology, but to the human mind at its most brilliant. If you enjoyed this deep dive into Victorian engineering, hit that subscribe button and turn on notifications. Next week, we're exploring the massive engineering projects of ancient Rome that we still can't fully explain. Have you visited any of these bridges? Let me know in the comments which one you'd most like to walk across. Thanks for watching, and remember, the past is more advanced than you think.